In this video, we'll talk about polar equations, which is the way we're going to start looking at trying to model curves and functions in polar coordinates. So the main way we think about functions in polar coordinates is the form r equals f of theta, right? Our method from Cartesian coordinates was y equals f of x. Here instead we have r equals f of theta. We want to visualize the radius as a function of what angle theta you're at. So theta here is your independent variable and r is your dependent variable in this case. The main things you want to think about when we're trying to figure out what these equations look like is you basically want to use the conversion formulas and plug them into your different equations to see what you get. As the first example, let's look at finding the equation of the line y equals 2x in polar coordinates. So to do that, I'm going to use my two conversion formulas for y and x, plug them in, and see what happens. Since I know that y is r sine of theta and x is r cosine theta, I can just plug these in. And so I then get that r sine theta equals 2r cosine theta. The r's actually cancel here. And I get that sine theta over cosine theta equals 2, or tangent of theta equals 2 for this function. More directly, you can write this out as theta equals inverse tangent of 2. This one doesn't work out in the r equals f of theta sort of format, but for this case, it makes sense. What's this function look like? Well, this function is the line y equals 2x. It's a line through the origin. What does that mean? That is the graph of a function of the form theta equals c for some value c, because our theta constant curves were just raised out of the origin. So this fits the model of a curve where theta is held constant. And so in this case, this sort of makes sense as what you should get for this sort of graph. It should be theta equals a number. The number is determined by the slope of this line because it's going through the origin. For a slightly more involved example, look at a different line. Look at the line y equals 3 minus 4x that I now want to convert into polar coordinates. Let's do the same process as before. Let's plug in r sine theta for y and r cosine theta for x and see what I get. So I end up with r sine theta equals 3 minus 4r cosine theta. Now I really just want to solve out for r here, because if I can write r equals f of theta, that'll give me a way to write this equation. So we'll move this to the other side. We get r sine of theta plus 4r cosine of theta equals 3. Factoring out the r and then dividing by the rest gives me r equals 3 over sine of theta plus 4 cosine of theta. And that's a way you can write the equation of a line in polar coordinates. Now you'll notice the equation we had up top, 3 minus 4x, is much simpler than what I have here on the bottom. And that's sort of to be expected because the constant curve lines for rectangular coordinates are all straight lines. I'm trying to model a straight line here. My constant curves for polar coordinates are all circles, so modeling a straight line is a lot harder, and we get something like this. You can do some more work here to make this a more general form, and what you get is that for a straight line, the polar coordinate form of the equation is r is d secant of theta minus alpha, where the nearest point on the line to the origin is at polar coordinates d and alpha. You can visualize that in this form because secant is 1 over cosine. I can use the fact that I have a sine and cosine here on the bottom to convert that into a cosine of a difference with a single argument in it, and then if I convert things appropriately, I'll see it fall out into this form. It is more tricky, it is more complicated, but you can do lines in polar coordinates as well. This sort of also hits the point that some equations are better in rectangular coordinates, namely those of straight lines. Although there are other equations like circles that are much easier in polar coordinates, and that's where you really get the benefit out of these sorts of setups. When the system benefits it, the polar coordinates become really useful and really helpful. When it doesn't, you're sort of forcing polar coordinates in where they don't belong. That's when you get up with equations like this. So that's the basic idea of polar equations and how they work. The idea being I want to write r as a function of theta because that's how I want to view what these equations look like. And that'll give us a way to analyze them going forward when we start trying to do calculus on these sorts of functions.